So let's now bring our discussion to the variable stars. We're going to repeat ourselves a little bit, going through what's going on in the internal structure of these high mass stars. So remember what I said last time, that the stars are layered like an onion. You're going to have a core of denser material, and surrounding that is going to be shells of lighter material. Right? So as we go through these fusion stages, they're going to evolve more rapidly in time. The heavier the material, the quicker we run out of that. You'll see this comment that when we get to like silicon burning, that takes days. Hydrogen burning, millions to billions of years. Silicon, days to get through. That is the range and time scales of how quickly the stars can run out of fusible material. What will eventually happen is that the stars reach what's called this instability gap. And when they do, they pulsate. They pulsate. The star will collapse in and expand out in a periodic fashion. Now, what's powering that is helium upwards towards the surface. What's happening is that helium is ionizing, having electrons stripped away from it, and then that helium cools off enough to recombine with electrons that are flying around. So you got helium atoms spitting electrons off and capturing them, spitting them off, capturing, spit, capture, spit, capture. And this process, this helium ionizing and then recombining, is helping with the pulsation of these stars. So, recap of that onion, these different layers. Look at these time frame of how long each layer is burning. Hydrogen and helium are on the scale of 7 to the 6 millions of years. This is a star that's 25 solar masses. Helium to carbon, 700,000 years. It's slower, about an order of magnitude slower. Carbon to oxygen, 600 years. We're starting to get dangerously close to a human lifespan. Oxygen to silicon, months. Silicon to iron, a day for a mass of this size. And then this core collapse, this catastrophic event of the core collapsing in on itself. Fraction of a second. In our next section, we'll go through this process in excruciating detail, because this is the source of big supernovas. But let's cut back. Let's not go through the whole life of the star. Let's go back to that variable stage, that pulsations, right? A couple examples of these. One type is called the Cepheid variable stars. Another type is the RR Lyrae variable stars. But it's the same principle that we're going to see. Basically is that if we look at a plot of time, how much time has transpired, and the luminosity of the star, we're going to see that it periodically goes up and down, up and down, up and down. Some of them can have a wide range of periods. We'll find periods that are some between hours and others that are years. There's a bit of a range in these. But the emphasis, we're going to have these supergiants that are pulsating on the scale of days to months. That's what we're going to focus on. And we're going to start noticing things that, like how luminous a star is, its period's longer. Think about this. The more energy output the star has, the longer its period. And this trend is true no matter what type of Cepheid variable star we're looking at. As long as we increase the luminosity, the time it takes for it to go up and down also increases. This is what a trend we see across all variable stars. Now going to these RR Lyrae variable stars. They fall into this discussion, but they are not high mass stars. They're actually low mass stars. They're on the horizontal branch. They're going to be less luminous than our Cepheid stars, but same principles are applying here. Some mechanic is causing them to pulsate in time. So, just to test if everyone's been paying attention, I'm not even going to pause this. We're just going to go through this quickly. What mechanics are driving the pulsations in the Cepheid variables? It's that ionization and recombination of helium. I put this question here because I really want to emphasize how important this is. This is what's driving that pulsating reaction. So let's do a little bit of history. Why do we care about pulsating stars? Why does it matter that we can see a star increase and decrease in luminosity periodically? Well, first observations were around 1596 by an astronomer named Fabricius, right? And he was looking at a star O Ceti, we now call it Mira, and he saw that the brightness of the star changed over the course of several months. This is a plot over the beginning of the last century, 20th century, 1900s. Gotta be specific now. All right. Looking at the brightness of that star over the period of several years. And yes, we do really see its luminosity go up, go down. What we now know is that Mira is in fact two stars, Mira A and Mira B. A is a red giant, AGB. Right? It's about a star of one solar mass, and it's got this companion, Mira B. So combined, Mira, it's this long period, right? It's about a year long for it to go up and down completely. The next observation, the second pulsating star found, was John Guttich's. This is around 1784. It was in the constellation itself, Cepheus. So we named the star Delta Cephi, and it oscillates in about 5 days. So we went from almost a whole year to 5 days. That's the range of potential pulsations that we can find in these stars. But same curve here. A couple of days have passed by, and the luminosity, they're applying the magnitude, but brightness, distance, you get the luminosity. So you look at the brightness go up, go down. So now astronomers are starting to establish, hey, there are stars that can change in their periods. And it's not just Earth moving in position. It's not just Earth changing where we are and our perspective shifted. No, it's literally the stars that are pulsating. Now, the first person to really formalize this was Henrietta Swan Leavitt. And what she was doing was looking at photographic plates. In essence, take your picture, click, and burn that image onto these photographic plates. And so what Leavitt did was take dozens and dozens of these plates and start stacking them on top of each other so that she could visually detect the star's brightness change over these days. She was comparing specifically the brightness. And she looked in a very special region of the sky called the Small Magellanic Cloud. Guys, I'm sorry, I'm always going to butcher that pronunciation. So I'm going to shortcut and call it the SMC. Right? Emphasis. Leavitt was looking in the SMC, and this is a cloud, a colloquial group of stars, and they're about 61 kiloparsecs from Earth. And this is the crucial insight. Leavitt was looking at a bunch of stars that are all approximately the same distance. All about the same distance. Right? Looking at this part of this galaxy and saying all these stars, finding pulsating stars, all about the same distance from us. So here comes the key insight that Leavitt had found. First, she was widely successful with her work. She found over 2,000 classical variable stars, and she found periods between 1 to 50 days, so 1 day to 3 months. And she noticed this pattern of, hey, the brighter, the more luminous the star is, the longer its period. And here comes the key insight. With all these stars in the SMC, if we can figure out how luminous they are, right, knowing their luminosity is going to help us tell distances. We're starting to build what we call standard candles. All of this is going off of this idea that the more luminous the star is, the longer its period. More luminosity, the longer the time it takes for it to go through its orbit. So tying this all together, like I said, distance of the stars in the SMC is about the same. And those variations in brightness is basically a measure of the luminosity. And if I know the luminosity, I can calculate the distance to that star. So Henrietta's work, looking at photographic plates and identifying these variable stars and looking at all these variable stars in the SMC, is now giving us a standard tool to get distance measurements. And this is one of our first steps to really measuring the size of the universe.